So today we're going to be starting your mass spectrometry, and this is an analytical technique used in forensic science to identify unknown substances in many different criminal cases. So in our previous topics, we were looking at your IR and your UV spectroscopy, and that was really looking at the interaction between your given particles and your radiated energy. Now we're looking at your mass spectrometry. So not the spectroscopy, the spectrometry. Okay. And this is a destructive method because we're ideally bombarding or breaking apart your sample into smaller fragments and then using those smaller fragments to identify your unknown sample. Starting off with your mass spec diagram. So first off, we have your sample that is vaporized, meaning it's in its gaseous state, and you're injecting it into your machine. The first part of your process is your ionization. In this process, the sample is bombarded by high energy electrons, and these high energy electrons are attacking your sample and knocking electrons off the atoms of your samples. Whenever you are removing an electron, you're producing a positive ion. In the ionization step, let's say your sample had contained sodium. Once it is bombarded by these high energy electrons, it knocks off electrons from the sodium atom, leaving your positively charged sodium ion. The next step is your acceleration step. The positive ions that you produce in your first step are now accelerated or pushed forward into your machine using electrically charged plates. These plates are negatively charged. So these negatively charged plates are attracting your positively charged ions. So this is going to cause your different ions to move faster towards your system. Once it gets to your deflection region, your ions are deflected based on their mass and also their charges. The lighter your ions, the greater the deflection, and the higher their charge, the greater the deflection. So whether or not your ions are just a +1 charge or a +2 charge, that would affect how much the ion is deflected throughout your machine. So typically, your mass to charge ratio of your ions are a +1. So most of your ions passing through your mass spec will have a charge of +1. That means that the only thing that is affecting their deflection is the mass of your ions. So because your ions are +1, the mass to charge ratio will be the same as the mass of the ion. Once your ions have been deflected, some more than others, they're going to reach that detection phase here. Right? So the machine electrically detects the presence of your different ions. Okay, and once it detects the ions, it's now going to produce a chart comparing the abundance or the percentage or the amount of that ion against the mass to charge ratio. And because most of your ions passing through are carrying a +1 charge, the mass is the same as the mass to charge ratio. So this right here is your chart output from the machine. So you have the abundance or the amount of each of your ion in a percentage versus the mass of the ions. It contains an ion that has a mass of 100 and an abundance of around, let's say, 40%. So once you know your fragments, you can then determine the overall structure of your sample. When it comes to your mass spectrum charts, there are a few terms that you have to be familiar with. Right? The first term is your molecular ion peak or your M+. So this appears at the highest value of your mass to charge and gives the molecular mass of the compound. You're looking at your M/G. This stands for your mass to charge ratio. Or since your ions are +1, it stands for the mass. And this is your highest M/G And this is going to tell you that your unknown sample has a molecular mass of 46. Next, you have your base peak. And the base peak is the tallest or the highest relative abundance. Now we're looking at this side of your axis. So you're looking at your percentage. So your base peak is the tallest / the highest relative abundance. And this indicates your most stable fragment. And it's usually given an arbitrary value of 100%. The height of all of the other fragments are measured relative to this. So this is your base peak here. Lets you know that your fragments with a mass of 31 is your most stable fragment. Here on your chart, here on your spectrum, you have your M plus peak identifier ready. That is telling you the molecular mass of your sample. Now we're introducing your M plus 1 peak. And this is a small peak next to your M plus peak. M plus 1 is caused by the presence of one carbon-13 isotope. So for example, let's say that you have a spectrum for your methane, your CH4. Oh dear Lord, it's 4 now. Come on, goodbye. Let's say you have a bunch of methane molecules, 1 out of every 100, instead of you having your carbon 12 here attached to 4 hydrogens, you would have a carbon 13 instead. So the presence of carbon 13 is indicated by your M plus 1 peak. For the part of your molecules that have a regular carbon 12, you would have our M plus peak of 16. So that would be the molecular mass of your sample, which is your methane. So your M plus peak would be your 16. Because every 1 out of 100 has a carbon 13 isotope instead of your regular carbon 12, those molecules would have a molecular mass of 17. And that is indicated by your M plus 1 peak. So just like your M plus 1, you also have the possibility of your M plus 2 and your M plus 4 peaks. And these are associated with your isotopes of your halogen atoms. Right? For examples here was your chlorine. So you have your chlorine 35 and your chlorine 37. This is also possible with your bromine as well. So your M plus 2 peak will be due to the molecular ion having a chlorine 35 and a chlorine 37, and then your M plus 4 peak will be a result of having 2 chlorine 37 atoms. So this is your mass spectrum for your chlorine. Here you have your chlorine 35 and here you have your chlorine 37. This here represents your molecular mass of your compound if you just had your chlorine 35 isotopes only. 35 and your 35 peak, and then we have your 35 and then we have your 37, and then lastly we have your M plus 4, which is your 37 and your 37. And the next example is your bromine. That is another halogen, and for your bromine you have 2 isotopes, your bromine 79 and your bromine 81. It's important to note that your M plus and your M plus 2 peak will be seen at relative percentage abundance on your bromine spectrum, whereas on your chlorine you saw that each different isotope combination gave you a different percentage abundance. Right, so here we have your bromine spectrum. So similar to your chlorine, starting off with irregular isotopes. Alright, every bromine 79, every bromine 81. Right. So over here you're gonna have your M plus peak, your M plus 2, and your M plus 4. So for your 158, your 79 and your 79. For your 160, you have your 79 and your 81 and your 81 isotopes. Overall, your mass spectrum identifies your unknown sample, whether that's a literal poison, a forensic case, or whatever it might be. So that sample is bombarded with high energy particles and broken up into different fragments. So here you have your mass spec, where you have your different fragments appearing in the mass spec for your given 2-methyl butane at varying abundance at the appropriate mass to charge ratio of your hydrocarbon, your 2-methyl butane. This sample, once it goes to your mass spec machine, is broken down into different fragments. On this spectrum, it identified your 29, your 43, 47, and 72. So I'm just going to try my best to do the structure of this molecule. To get your mass to charge ratio, your mass of 29, it involves breaking apart your fragment at this point right here. 2 carbons with a mass of 12. So that is your 24. And then you actually have your 5 carbons along with that on this carbon. So it's split here and you don't have that final 4th bond right there for your carbon. What you actually end up having is a plus charge right there to indicate your fragment and to indicate that there is 3 instead of 4 bonds for this carbon right there. So this fragment is equal to your 29. The next one is your 43, and this 43 is actually at your highest percentage relative abundance. So this is your base ion peak and is therefore your most stable peak. That 43 actually came from your 3 carbons and your 7 hydrogens. Remember, you had this initial split of one of your 2-methyl butane molecule, right? That split right there. That gave us the 29 fragments, and the other side over here is giving us your 43. And because right here is where your fragment split, this carbon here is going to be missing a bond. So you're going to have a plus by that carbon. So in this case, you have 3 carbons, that's your 36, and then you have your 7 hydrogens. So 1, 2, 3, 4, 5, 6, 7. So that gives you your 43 in your mass to charge ratio. So your next fragment is your 57. This last bar here is at the highest mass to charge ratio. So this 722 here actually represents the molecular mass of your 2-methyl butane. Have your 5 carbons and your 12 hydrogens. So your last fragment is looking at your 57, and this is actually 4 carbons and 9 hydrogens. So if your molecule was to split on this side here or split on this side here, it just removes one of your carbons. So then you have your 57, and that's gonna give you 1, 2, 3, 4 carbons. And on this side where your fragment split, you would have a plus to indicate that there's a loss of a bond for your carbon. Okay, so this is the question that we're gonna look at in our next class, and then we're gonna look at some different mass spec examples and work through them.